of this tree, then from here, what's the next thing in order? The next thing in order is this. So it's you go down one, and then you go all the way down here. So it's the in-order successor is what it's talked about. And this is the in-order predecessor. And that's what you're trying to swap. You want to find the in-order successor, and you swap that with the node you're trying to remove, and then that will be a leaf, and you can remove it. That's what you're trying to do. And I don't know why that other one is so broken. Okay.
It's not a checker 60.
Why is this not? Final node is just a single search. Do and save it. Now, I told you I was going to tell you an interesting story about this. This is where I get to that. So, after I learned about trees, I thought they were super exciting because I could store a big list of things and I can get login search time on it. That seemed pretty slick. And it was using pointers, which, being a fresh new computer science student, I thought I was pretty smart because I could use pointers. And it used recursion, which made me doubly smart because I could use recursion. So, I mean, it had all the hallmarks of being totally geeky and the best thing to do. So, I was also a super geek because, or maybe it's a nerd, I don't know. When I was in high school, I also had a stamp collection.
Dude, it's so radical.
Well, the reason I had a stamp collection is I told my brother one day, we should have a hobby. I only know of two of them, stamp collecting, coin collecting. Which one do you want to do? And he said, I don't care. I said, well, stamps are easier to get. So we'll do stamp collecting. I didn't really care about it. I just knew I had to have a hobby because apparently everyone does. So, anyway, I decided that I wanted to use, this was actually in college now, I decided I wanted to store all of the information, which was my stamp collection was small. But I wanted to store all my stamp information into a database like this so I could search it really easily. So I wrote a program that had a nice little tree, a binary search tree, and I could add new data records and it would stick it in the tree. And obviously I wanted to save that information. Well, what's the coolest traversal? In order, right? That's the coolest traversal. So what would happen is when I was done entering data and I hit save and I exit my program, I had my nice pretty binary search tree with all the data, and I would do the coolest thing possible. I would do an in-order traversal of my data and I'd write it out to the file. And when I would open my program back up, I'd read that data in and recreate my tree and everything was great. Well, I noticed as I was going along that after entering more and more data, it was slower and slower to do anything. And I was like, that doesn't make any sense. It shouldn't get slower and slower. So I investigated a little bit more, and I discovered that when I did an in-order traversal, I was writing everything out in order, right? Then when I would read the file back in, I would read the first item. I'll just, to simplify, say first item had ID 1, so I'd add that to my tree. The second would be ID 2. So where does that go?
To the right.
Then the next one would be ID 3. Where does that go?
To the right.
And so on. And so eventually I figured out that my super tricky program would create a bind, then I would add some data.
Save.
Then I would save, and I'd reload it, and it vinified it all.
Yep.
Right? So it was not a successful strategy. Once I figured that out, I don't remember what I did, but I was like, oh, so in order is not always the coolest thing. Instead, when you are saving things out, you should use pre-order. Do a pre-order traversal of your tree when you write things out. Then your nodes go out in pre-order. When you read them back in and you insert them back into your tree, they will, I will double check this, but they come back in and it creates the same shape as what you have.
And it always inserts on the bottom.
And so,
Never has to break.
okay, let me see if that's true. So everyone tells me, and and I've never verified it because I didn't remember this when I was back then in college writing this. So like I said, I don't remember how I saw it. But my pre-order in this is going to be 60, 20, 10, 40, 30, 50, 70. So that's my order. Now when I read them in, I'm going to get empty tree. I get 60, goes at the root. The next thing I get is 20, and that goes over here. The next thing I get is 10, and that ends up over here. The next thing I get is 40, that's the 60, and that ends up here. So it does end up recreating the same tree that I had. So, pop quiz again. This is for 5,000 points. What is the best use of pre-order traversal?
Saving a creation.
Saving a tree to a file so you can recreate. What's the best use of in-order traversal?
Destructor. Oh, in order printing.
Creating a vine. So what was the best? Well, yeah, sorting or getting things in order. And then post-order?
Destructor.
So they all have their uses. But saving to a file, you write it out in pre-order, and when you read it in, you can just use your normal insert routine. One of the things you do not want to do is when you save the tree structure to a file, don't save the pointers. Just save the values in the nodes, and you do it in pre-order as a pre-order traversal. When you read it back in, you can just use your same insert algorithm. Now, the reason you don't save the pointers is because the next time you run your program, it might end up in a different spot in memory. So your pointer values don't make sense anymore. So, yeah, you never save pointer values into the file.
Insert pointers into the file. That's interesting.
Okay, a couple slides on general trees, and then we're done today. All right, so general tree, done with binary trees for the moment. General tree is this. General tree has any number of nodes, not just limited to 2 max. So in this case, A has 3 nodes, or 3 subtrees, B has 3. There's nothing that says that, B could have 17 with A3. It doesn't matter how many. The general tree just says that it's kind of a free-for-all for the number of children. The only requirement is just as I've shown that every subtree is still a tree. So there are different ways to implement this. One interesting way is with the binary tree. Now I want to point out this is my tree, A, B, C, D, E, F, G, H, I. I can use a binary tree to implement this. Notice that I have a binary tree here. What I've done is I use the left child, this is left, right? Left child points to the descendants of A. The right child points to siblings at that same level. So A was my root, and I have the descendants, so I point to B, and B has descendants that point down here, but this points to all the siblings at that same level. So this turns out to be a binary tree, right? I have on these nodes that have 2 children at most. And notice that B points to E and F and G, but not to H and I, because those actually are under D. Right? H and I are under D. Okay? Now once you get this structure, you can grab A, shake it a little bit, and your tree restructures to look like this. But that's the same thing, it's that binary tree. But now I can do all the binary tree kind of things. This is not a BST. It's not a binary search tree. There was nothing about this that said binary search. And in fact, with the general tree, there's no, what does a search tree even mean, right? B is between E and F, or B is between F and G? You don't know. All right, so the whole search tree concept doesn't work for a general tree like this. But you can, as I showed, you can represent this as a binary tree. Then all your normal binary tree algorithms will work. Insert, delete, all those things will work. But it's not a search tree. Another option is instead of using a binary tree encoding, you can use a linked encoding. So each node just has multiple instead of two, has multiple things. Now, one thing I recommend if you're doing this, which I kind of like this better than the other one, this one is, I understand the concept, but it twists my brain a little bit. This one is pretty straightforward. The only thing that I would caution you is if you're ever doing this, don't hard code these as separate links. Make an array of links. Because as soon as you do it, you say, I can have most three, and so you have left, middle, right, then you know what happens, right? Someone says, oh, that's so great, we want 4. And now you have to go change all your code to handle 4 nodes. Left, middle 1, middle 2, and right. Or whatever you want to call them. So instead, if you start by making this an array of pointers, then all the places where you have to process this, you just have a for loop that goes over all of your pointer things. Okay, that's it. So,